Hey folks, my name is Nathan Johnston, and welcome to Lecture 13 of Introductory Linear Algebra. Today we're going to start learning about something called linear transformations. And what these are is they're functions that send vectors to vectors. Okay, so for example, if you've got a vector with two entries, then a linear transformation just takes that vector with two entries and moves it somewhere else. Okay, so it spits out some other vector. Okay, so it's got your vectors as inputs, and that gives you vectors as outputs. Okay, and I mean, it might send a two-dimensional vector to a two-dimensional vector, it might send a three-dimensional vector to a three-dimensional vector, or it might mix and match dimensions as well, like it can send a two-dimensional vector to a seven-dimensional vector. Okay, but it turns out that studying all functions that send vectors to vectors is too complicated, okay? There's just no hope of having nice theorems that say, well, if you've got a function that sends vectors to vectors, then this happens. It's just too wild of a set. Okay, so what we do is we restrict our attention to functions that send vectors to vectors, but do so in a nice way. They have to send vectors to vectors in a way that basically plays well with other linear algebra things. Okay, and this is going to let us prove nice theorems and do nice things with these functions, because we're only going to look at sort of the simple functions that send vectors to vectors, and these functions are linear transformations. Okay, so that's enough of that. Let's get to the actual definition. What is a linear transformation? Well, just like I said, a linear transformation is a function, so it's sending n-dimensional space to m-dimensional space. Okay, those dimensions might be the same, but they might be different too. Okay, but it's not just any function sending n-dimensional space to m-dimensional space. It's got to satisfy these extra two properties down here, these properties that I've called A and B. And basically what these properties say is the function plays well with the standard linear algebra operations, okay, with the standard operations on vectors. Remember, we've got vector addition and we've got scalar multiplication. And, well, basically the two properties of linear transformations relate to those two operations. Okay, so the first property here, property A, says that if you add two vectors and then apply the linear transformation to that sum, you get the same thing as if you apply the linear transformation to the vectors and then add them up. In other words, in a sense, like applying the linear transformation, it kind of commutes with vector addition. You can do them in either order and you're going to get the same answer. Okay, then property B is the analogous thing for scalar multiplication. You can scalar multiply and then apply t, or you can apply t and then scalar multiply, and you'll get the same answer either way. You can do it in either order. In other words, you can pull scalars out of the function. Okay, all right, so before we look at specific examples of linear transformations and do things with them, I want to sort of draw a geometric picture of what they're doing, okay? And I'm going to convince you of this geometric picture, hopefully at least, by the end of today's lecture, okay? But for now, I'm just going to draw it, and then I'll try to convince you of it later. All right, so let's draw a picture, well, in 2 dimensions, because I can't really draw pictures in higher dimensions. Anyway. All right, so in 2 dimensions, let's start off by drawing 2-dimensional space. And I'm going to overlay a grid, a unit square grid, on 2-dimensional space just to make it a little bit easier to visualize after I apply the linear transformation to it. Okay, so here's 2-dimensional space. I've drawn this unit square grid here. And I've also highlighted one particular square here, and that is the square that has E1 and E2 as its sides. Remember, these are the standard basis vectors. This E1 is 1, 0, and E2 is 0, 1, so it just points up a distance of 1. And then I sort of highlighted in yellow here, sort of that first square in the positive quadrant. Okay, now if I apply a linear transformation to this space, I'd like to know what space looks like after I apply this linear transformation. And in particular, I'm going to focus on what it does to E1 and E2. Okay, and in a sense, I don't know what it does to E1 and E2, right? I mean, it's just some general linear transformation. It's some function, so it can send E1 wherever it wants to. Let's just imagine that it was sent over here. And it can similarly send E2 wherever it wants to, okay? So it can send those two vectors to anywhere. But then the point is, once you know what happens to E1 and E2, once I know, oh, here's T of E1 and oh, here's T of E2, then you know what happens everywhere else. Because what linear transformations do is they send this unit square grid into some parallelogram grid, okay? And that parallelogram, it just has sides T of E1 and T of E2. So in other words, this linear transformation, it's just taking this square grid here and it's sort of stretching it. Okay, it's sort of stretching and deforming it into a parallelogram grid. And you know, what parallelogram grid gets made? Well, that's just determined by these two vectors here that you have to compute. Okay, but the point is, once you know what happens to those two vectors, you know everything. So for example, then if I give you another vector, if I say, okay, now I'm interested in what happens to this vector v here. Okay, well then what you can do is you sort of notice that, oh, okay, hey, it's over in this pink square over here that's sort of 3 squares in the E1 direction and just 1 square up in the E2 direction. Then, well, this vector v, it's going to get sent over 3 squares or 3 parallelograms now in the t of E1 direction and 1 square in the t of E2 direction. So it's going to get sent over there. Okay, so it just sort of stretches and deforms every vector sort of in the same way. It's very uniform in this sense. Okay, we'll come back to that in a little bit once I've hopefully maybe actually convinced you that this picture is true. But for now, I want to sort of give you another way of thinking about linear transformations, and that is, well, they were defined as functions that preserve vector addition and scalar multiplication. And remember, if you combine vector addition and scalar multiplication, what you get are linear combinations. So another way of thinking of linear transformations is they're exactly the functions that sort of preserve linear combinations. They're exactly the functions that you can pull linear combinations out of. Okay, so in other words, they're exactly the functions with the property that t of linear combination equals that same linear combination, except with t applied to each of the vectors individually now, right? So I've just sort of pulled each of the c's out and each of the sums out, okay? And I've applied t to each of the vectors on the inside here. Okay, and sort of split it up as much as possible. For most functions, you can't do that, okay? For most functions, this is not a true equality, but for linear transformations are special. Linear transformations, this is true, okay? No matter what scalars you pick and no matter what vectors you pick. All right, so let's go through a couple examples. Let's actually see some linear transformations. So which of the following functions are linear transformations? So first example, suppose you've got some matrix, okay? So I give you some matrix, it's an m by n matrix. Then I can define a function based on this matrix. And what I'm going to do is I'm going to define a function just via matrix vector multiplication, okay? So I'm going to think of my input vector v as a column vector, and then I'm just going to take that column vector and multiply it by some fixed matrix A that's given to me. Okay, and when I do that, well, if I'm thinking of v as my input n-dimensional vector as a column, then this is going to be an m by n times an n by 1. Okay, so at the end of the day, I'm going to get an m by 1 column vector after I do this matrix multiplication. Okay, so I'm going to get something in m dimensions after I do this. Okay, and then the question is, yeah, certainly this is a function, right? It's a rule for sending n-dimensional vectors to m-dimensional vectors, but is it a linear is it a linear transformation? Does it satisfy those extra 2 properties? Okay, so those properties that we called A and B in the definition of a linear transformation. So let's check those. Okay, so let's check property A to start with. So I'm just going to scroll back up, remind you of what property A was. Property A was, well, does t of v plus w equal t of v plus t of w? Okay, well, let's check that. Okay, so I start off with t of v plus w, and I want to show that this equals t of v plus t of w. Okay, well, I mean, t of v plus w, just by definition, just plug in the definition of your linear transformation, and, well, t of v plus w equals a times v plus w. Great. Okay, but now what I can do is, I mean, this is a matrix multiplication, and last week I learned all sorts of things about matrix multiplication. I know all of the nice properties that it has, and in particular, it has left distributivity, right? We had a theorem that said, yeah, if you have like a matrix A times B plus C, you can split that up as AB plus AC. Okay, so that's the theorem I'm using here, a theorem from last week. I can split this up as AV plus AW. Okay, and now I just say, oh, wait. AV, that's just T of V. And AW, that's just T of W. And that's exactly what I wanted. I've got T of V plus W equals T of V plus D of W. Great. Check mark, because property A, now I see it's satisfied. Okay, so it's just using the definition everywhere and then using things that we know about matrix multiplication in the middle. All right, next, to see that property B holds, we do the same thing with scalar multiplication. T of C times V, I want to show that that equals C times T of V. All right, so how do I do that? Well, again, I'm just going to use the definition and then things that I know about matrix multiplication. So start off with the definition of T. Well, T of CV equals A times CV. Okay, and now use things that you know about matrix multiplication. And in particular, the relevant thing that I know here is that if I have a matrix times a scalar times another matrix, I can pull that scalar out in front. Okay, so again, this is just from a theorem from last week, one of our theorems that told us properties of matrix multiplication. Okay, And now AV, oh good, that's just T of V again. So I can substitute back in via the definition, and I get exactly what I wanted. Okay, so property B of linear transformations is also satisfied. So then because both of those properties A and B are satisfied, yes, T is a linear transformation. No matter what matrix you give me here, yeah, this function is a linear transformation. T of V equals A times B is a linear transformation. Great. All right. Next up, how about this function that sends two-dimensional vectors to two-dimensional vectors via this formula here? Okay, so it sends the vector xy to x minus y, x plus y. All right, so let's show that this is a linear transformation as well. All right, so again, there are two things that you got to check. You've got to check that T of V plus W equals T of V plus T of W. And you've got to check that T of CV equals C times T of V. Okay, so it plays well with addition and scalar multiplication. So let's start off with addition. And again, just plug into the definition everywhere. T of V plus W, well, because this formula is defined in terms of the entries of the vector, I'm going to write this out a bit more explicitly in terms of the entries of the vectors. Okay, so V is V1, V2, W is W1, W2. Okay, and now I'm going to actually add those up. Okay, V1, V2 plus W1, W2 is this here. First entry is just V1 plus W1. Second entry is V2 plus W2. Vector addition is just entry-wise. That's all I did there. And then this next step, now I'm using the definition of T, right? And the definition of T is, well, the output of T of something is just first entry minus second entry, and then first entry plus second entry. So that's all I'm doing here. I'm taking the first entry, V1 plus W1. I'm subtracting the second input, V2 plus W2. Okay, and that gives me my first output entry. And then my second output entry is just you sum up the two inputs. So V1 plus W1 plus V2 plus W2. Okay, and I could probably simplify that a little bit and reduce it or whatever, but I'm just going to leave that there. And now what I'm going to do is I'm going to sort of work from the other side. I want to show that this equals T of V plus T of W. Well, let's just start with T of V plus T of W and see if we get the same thing after we simplify a bit. T of V, well, I mean, just use our formula here. It's V1 minus V2 in the first entry and V1 plus V2 in the second entry. And then T of W, same thing except with W's, right? It's W1 minus W2 in the first entry, W1 plus W2 in the second entry. Okay, and now just use your definition of vector addition here and add things up. Okay, so just the sums of the first two entries, V1 minus V2 plus W1 minus W2. Okay, and then V1 plus V2 plus W1 plus W2. Okay, so just add things up entry-wise. Okay, and then from here, all you do is you stare at things really hard. Okay, I want this to equal this. And do those equal each other? Well, let's see. I've got a V1 here, a V1 here, minus V2, minus V2, a plus W1, plus W1, minus W2, minus W2. Yeah, I mean, you just stare at it and match up all the terms. Yeah, every term that's down here is up here and vice versa. Okay, they're the same thing. They're just written slightly differently. Okay, so those two vectors are the same. So yay, we're happy. Property A holds. All right, now just do the same thing for property B. Show that you can pull scalar multiplication out of it as well. Again, just use the definition everywhere, okay? T of C times V is, well, okay, what is scalar multiplication? Well, you just multiply each of the entries by the scalar. Okay, so C of V1, C of V2. And then what is T of this? Well, just go back and use your definition of T. It's gonna be first entry minus second entry, and then first entry plus second entry. All right, so C of V1 minus C of V2. Sorry, CV1 minus CV2, and then CV1 plus CV2. Okay, I've just used the definition of T there. And now I just noticed that, hey, there's a C in every single entry there. I can pull that out in front because that's what scalar multiplication is, right? So this is just C times V1 minus V2, V1 plus V2. And then I look at this and I say, oh, hey, great. That's just exactly what T of V1, V2 is. I just use my definition of T again. And then I'm done, because that's what I wanted to show. And now I've shown that T of C times V is the same as C times T of V. Okay, I can pull that scalar out. So great, because both of these properties are satisfied, that's a linear transformation as well. All right, let's do one last example here. This time, It's a linear transformation from 2 dimensions to 2 dimensions again, but this time it's going to be defined by this weird formula here. So this time it's sending the vector xy to 3 times x squared plus y, and then 2x minus 4. So again, this is a function, right? It's a function. It's a rule for sending 2-dimensional vectors to 2-dimensional vectors. The question is it a linear transformation? Does it satisfy those 2 extra properties that basically, say that it's nice, say that it's, something that we can study with linear algebra? Okay, and for this one, I mean, very naively, I just look at this x squared, and that sort of makes me a little antsy, right? Okay, because when I see that x squared, I'm not thinking linear. That doesn't feel like a linear thing, right? That's a quadratic. It's a, if I was to graph just x squared, that's a parabola. Okay, so it sort of doesn't feel linear in a sense. It feels like it's just violating the terminology linear transformation. So instead of trying to show that this is a linear transformation, I'm thinking it's probably not a linear transformation. Let's show that it's not a linear transformation instead. Okay, let's really try to pin that down. Let's convince ourselves that that's true. Okay, so how do you show that something's not a linear transformation? Well, you have to show that at least one of the 2 defining properties does not hold. So we go back to these 2 properties here, A and B. I want to show that at least one of them fails. Okay, so that just means I've got to find some particular counterexample for either property A or for property B, right? Like the opposite of A happens for all vectors is A does not happen for some vector. Okay, so I've just got to find a particular counterexample. Okay, and it turns out, I mean, if you want to show that something's not a linear transformation and you're trying to find a counterexample, most of the time you can just pick them randomly, okay? And, if there are counterexamples, they'll usually be very easy to find. So I'm just going to make up some vectors randomly here. Okay, v equals 1, 1, and w equals 2, 3. Where did those come from? They came from just random places in my head. Okay, it does not matter where they came from. Okay, I made them up randomly. And then I'm just going to check, do the defining properties of a linear transformation hold for these 2 vectors? Okay, if they do hold, it tells me nothing, unfortunately. But if they don't hold, then that's a counterexample that shows it's not a linear transformation. All right, so t of v plus w. So for this one, what I've got to do is I've got to add v and w first. Okay, so 1, 1 plus 2, 3 is 3, 4. So I want to do t of 3, 4. Okay, how do I do that? Well, I just plug into the definition. X is 3, y is 4. All right, so it's just 3 times x squared. Well, that's 3 times 3 squared. And then plus y plus 4. All right, 2 times x, that's 2 times 3 minus 4. Okay, and then I just compute those things. I get 31 in my first entry and 2 in my second entry. Great. Doesn't tell me anything yet, but now what I'm going to do is I'm going to compute t of v plus t of w and compare that. And my hope is that I get a different vector. If I get a different vector, then I know it's not a linear transformation. All right, so t of 1, 1 plus t of 2, 3, right? That's t of v plus t of w. Okay, and all I do is I plug these numbers into the definition of t. So I plug 1, 1 in, so I'm going to get 3 plus 1 is 4 in the first entry, and then I'm going to get 2 minus 4 is minus 2 in the second entry, so that's t of 1, 1. And then t of 2, 3, well, that's 3 times 2 squared, so that's 3 times 4, that's 12. Plus 3, y is 3, so that's 15 in the first entry. And then 2 times 2 is 4, minus 4 is 0 in the second entry. Okay, and then I add those up, and I'm going to get 19 and minus 2 as my answer here. And then I just look at these 2 vectors here, and I ask myself, are those the same? And no, they're not the same, right? Okay, and because they're not the same, I know property A of linear transformations is violated. So no, like this is a function, but it's not a linear transformation. It's sort of not a nice function. And in particular, sort of what's going wrong with this function, what makes it not a linear transformation, is the fact that we've got a variable squared here, and actually also the fact that we've got this minus 4 here. In a linear transformation, you can only have scalars times variables and then additions and subtractions of those. So basically linear combinations of variables. You can have things like 3x plus y, but not 3x squared plus y. Okay, and you can have things like 2x minus 4y, but not just 2x minus 4. Both of those things cause problems. You also can't have things like x times y. You can't multiply variables. You can't do like cosine of x. You can't sort of do weird functions of variables. All of those things are disallowed. You can only do, scalar times variable plus scalar times variable, and so on in each of the entries of the output. And that's something that we'll prove in the next lecture. Okay. So now what we're going to do to round out this lecture is I'm going to go back and I'm going to try to convince you that that geometric interpretation of linear transformations that we talked about earlier I'm going to try to convince you that that's true. So that picture where we had a square grid get turned into a parallelogram grid. Okay, and the way that this works, the way I'm going to try to convince you of that, is remember that every single vector can be written as a linear combination of the standard basis vectors. So you can write it as, first entry of v times e1 plus second entry of v times e2, all the way up to last entry of v times en, where remember these e vectors, these standard basis vectors, those are the vectors that have just a single 1 in one of their entries and everywhere else is 0. Okay, so, well, if we use this fact together with the fact that linear transformations are the functions that preserve linear transformations, then what we get is, well, if t of some vector is t of this linear combination up here, and now we split it up because t is a linear transformation, then what we get is t of v equals its first entry times t of e1 plus its second entry times t of e2, all the way up to its last entry times t of en. Okay, and at first this just looks like a mess of symbols, but what this tells us is very important. This tells us, actually, this equation right here encapsulates the fact that unit square grid gets sent to parallelogram grid. Because, for example, in the two-dimensional case, so if n is 2 and the sum doesn't have this junk over here, it just has the first two entries, then what this is saying is t of v is sent to the vector that points v1 units in the direction of t of e1 and v2 units in the direction of t of e2. Whereas it used to be the vector that pointed v1 units in the direction of e1 and v2 units in the direction of e2. So all that happened, like it's still sort of pointing the same amount in these two directions, all that's changed is those two directions changed. It's no longer e1 and e2, now it's t of e1 and t of e2. Okay, so again, let's go back, show you that picture to try to sort of pin this down again. Okay, so v, it used to point, some amount in the e1 direction and some amount in the e2 direction. Now it points those same amounts in the t of e1 and t of e2 directions instead. So now instead of pointing over, 2.5 boxes that way and half a box up, now it points 2.5 parallelograms this way and 0.5 parallelograms up that way. Okay, so in other words, everything's spread sort of uniformly out by this function here, by this linear transformation. Another way of saying this is linear transformations, they have the remarkable property that they're completely determined by n vectors, okay? They're completely determined by t of e1 and t of e2 all the way up to t of en. If you know what a linear transformation does to the standard basis vectors, then actually, very remarkably, you know what they do to every single vector. That's enough to completely reconstruct the linear transformation, the entire function. Okay, and this is very, very different from functions in general, even functions of just one variable, of just a single real number, right? If you have a function of a real number, and let's say that you know that, f of 3 equals 4, and let's say that you also know f of 4 equals 7, and maybe you know a whole bunch of other points, any number of finite points, okay? You know f of 5 equals 19, and f of 6 equals -3, and f of 7 equals 48, okay? And that finite list is however long you like. Well, you still don't know what f is, okay? No matter how many individual data points you have, you still don't know what the actual function is because, you can find polynomials that go through whatever points you like, and you can find infinitely many, even just polynomials that go through any finite number of points that you like. Never mind even more exotic functions like cosine and sine and logarithms and exponentials, and functions that are even worse than that, things that aren't even differentiable. Okay, so linear transformations, they're really remarkable. You just need a finite amount of data to reconstruct the entire function. All right, let's go through one example of how to actually do this. Okay, so suppose we've got a function and we're told two things. We're told that it's a linear transformation, and we're told what it does to the standard basis vectors. Okay, well, if you have those pieces of information, you can reconstruct it entirely. So what we're going to do is, based on these two data points, t of e1 and t of e2, we're going to figure out what t of 2,3 is. And we're also going to construct a general formula for that linear transformation. So we're going to be able to compute t of v1, v2, no matter what v1 and v2 are. All right, but let's start off with t of 2,3, just to see how it works. All right, and the trick is write 2,3 as a linear combination of those standard basis vectors, okay? And we saw how to do this earlier in the course. 2,3 is, well, you just peel off those coefficients. It's 2 times the first standard basis vector plus 3 times the second standard basis vector. All right, and then you apply t to it, okay? T of 2,3 is t of this linear combination, because those are the same thing, okay? And now use the fact that it's a linear combination. A linear transformation. Use the fact that t is a linear transformation to split that up, okay? T of junk is 2 times T of E1 plus 3 times T of E2, okay? So we just brought the 2's and the vector addition outside of T because it's a linear transformation, so we can do that. Okay, and now, hey, T of E1, I know what that is. The question told me. T of E1 is the vector 1, 1. And T of E2, again, I know what that is. That's the vector minus 1, 1. Okay, so just make those substitutions. And now it's just scalar multiply and add them all up. And at the end of the day, you're going to get the vector minus 1, 5. Okay, so if you ever have any linear transformation that sends E1 to 1, 1 and E2 to minus 1, 1, then it must send the vector 2, 3 to minus 1, 5. Okay, there's no other possibility, or else it can't be a linear transformation. Like, it'll still be a function if it sends 2, 3 somewhere else, but it won't be a linear transformation. All right, so let's generalize this a little bit and figure out an explicit formula for T of V1, V2. Okay, so slightly more generally, if you have T of V1, V2, well, you can write V1, V2 as V1 times E1 plus V2 times E2. So just write that vector as a linear combination of the standard basis vectors, and then split that linear combination up again because T is a linear transformation, so you can do that. Okay, so this is V1 times T of E1 plus V2 times T of E2. Okay, and then just sub in what are these vectors here. What is T of E1? Ah, well, that's 1, 1. And what is T of E2? Ah, well, that's minus 1, 1. So just sub those in there. You get this. And then do the scalar multiplication and vector addition, and you find that T of V1, V2 must equal V1 minus V2, V1 plus V2. Okay, and this is actually a linear transformation that we saw back a couple examples ago. So this is exactly this linear transformation 2 that we saw right here. Okay, so as long as your linear transformation sends E1 and E2 to those particular vectors, then actually your linear transformation that you're working with must be this one. Okay, it's the only possibility. Okay, so we'll sort of explore consequences of this idea next class. And what we're going to do is we're going to show, okay, not only is a linear transformation completely determined by what it does to the standard basis vectors, but actually, once you've determined where those standard basis vectors are sent to, you can represent that linear transformation via matrix multiplication. You can construct a particular specially chosen matrix that when you multiply it by any vector v, you get the exact same thing as what that linear transformation does. Okay, so that's what we're going to do next class. We're going to see that linear transformations, really, they're just the geometric version of matrices. Matrices are algebraic, and we have all these sort of algebraic rules for how we multiply them and things like that. And linear transformations tell us sort of geometrically what they're doing. Okay, so I will see you next class when we sort of tie linear transformations together with matrices. See you then.